I'm back here and I have another coding story for you guys. So, as you know, Arjun was happy doing his Rust coding, and Rust being a very high level language. And besides, Rust was an awesome language with memory safety and all these things. But what was missing? Arjun wasn't happy with this illusion of high level that high level languages give him, even though it was a very safe world. And first of all, he missed the things he could do in C, even though they were dangerous things sometimes, and they caused crash dump, core dump, memory leaks, all those things. So the Rust was saving him, but the compiler was very strict, like a parent who is very strict and wouldn't let the kids do what they want to do. So he's been complaining. He was being unhappy with this illusions of the high level languages, and then he was complaining to Krishna all the time. And he kept telling Krishna to show him the reality, the ultimate reality, how things work at the machine level, not at this abstraction and not this imagination, and the piles of imaginations that we build and we start living in them. So since he complained a lot to Krishna, Krishna finally said, okay, we will do assembly language today. And thus Arjun became very happy when Krishna showed him the bits and bytes and the CPU registers. And Arjun's mind was completely illuminated when he came to know how things work. So we will see what happened. So then there comes, and how do we know all this happened? So Sanjay was watching all this dialogue between Arjun and Krishna, and thus we know what happened. So this is what basically Krishna told Arjuna. He said, we'll first write a hello world.asm program in Linux in x86 assembly, and we would do it at such a level that we won't use C library even at all. Forget Rust, we won't even use C library. And as Krishna laughed with a um, with his satisfaction was showing that being able to show the ultimate reality to Arjun. And he said that all these people who have been giving you these illusions of high level languages, they have been hiding the machine from you. And the machine today will be completely clear in front of you. You would know, thou shalt know this CPU architecture. And he said we would write a hello world in assembly where we would not even use C library functions. We'll go straight into system calls. And this is how things are happening here. So we have in assembly, there's always a data section and a text section where the code lives. And the data section is where your static data, global data as you call them in high level language lives. And that's inside the dot data. So as you can see what we are doing here, we have a string. This is how you declare strings in assembly language. You have to say at the byte level, you have to say what is this is the string. You could change it anytime. The string right now is Arjuna telling Krishna that no, x86 assembly is there, but Rust is easier. So that's your string. And we got strlen here is, don't be confused by this xtrlen being, don't think it is C library's strlen. It is just a label is calculating on the fly using these assembly directives the length of the string. In assembly, they can calculate the length of the string by just saying, hey, from the current location in memory, subtract minus str, and that's where you get the length of the string. So basically, you are at the current location in memory, current address, and then you're basically going to the beginning of the str minus str. Will give you the length of the above string. So here we are now. Here section text. Now let's see what is happening here. So EAX, move 4 into EAX. So why 4? What is so big deal about 4? What are all these magic numbers? 4 is write system call on Linux, and 1 is the exit code of the system call. ECX is where your string to or the buffer to be printed is there. EDX is where the buffer length is there, and this is the way you do make a syscall x86 way. So I know that things have changed a little bit in 64-bit, but in 32-bit x86, this is how we used to do by syscall by doing interrupt 80. And at this point, this will print this string that we just wrote. But if you want to, after that, exit cleanly, you have to do exit system call. For that, you have to put the exit syscall number. You put the return code, exit code in EBX, and again you execute system call. So let's see if it runs. And how do you run this? You got to have a package known as nasm. This is assembler on Linux, and then you got to say minus fel elf, and then you got to say hello world.asm. So he's saying number 1 label or is at the end of line. Let's see what happened. What did we do? So okay, section.data label at the end of the line. Did we make a mistake here? Section.text. It doesn't sound like we should have had any issues. So let's look at another ASM program if we have made any mistakes. So parity.asm. So maybe when we cut and paste we made a mistake, but basically hello world.asm should be alright. So .global .section.data. So again let's compile nasm minus f elf hello world.asm. Oh, I see. The problem was that by mistake we were giving hello world executable that was already there. Let's delete that. It was basically causing us trouble. We'll build it actually from scratch. So nasm minus f elf hello world.asm. The file was absolutely correct. There's no issue at all. Again, let's take a look. We have a section.data where we have the string, and then we just learned how to make system calls in assembly at the CPU level. As you know, this x86 has 8 general purpose registers: EAX, EBX, ECX, EDX, ESI, and things like that. So you got to be knowing. So here you got to know the architecture of the CPU, and that is where Arjuna was completely flabbergasted when he came to know the reality, when he saw the reality, and when he was exposed to the reality of the CPU, and then he was surprised at how much illusions he was living under. So when you did this, you got a file known as hello world.o. Yes, if you delete it, you see that the previous call, actually that's exactly what it does. if you see, if you do this, this actually create hello world auto nearlf. See, we have again deleted it. Okay, so you see ls minus l hello world auto, it creates it. So this is actually just created. Now we actually will build it. So how do we build it? We want to use GCC. We don't need GCC. We don't have a main starting point in our program. We'll use this call. And as you see, minus m is telling the architecture of the machine to the linker, and minus o is the out object file name, executable name, hello world auto. So let's see that. Okay, great. Now we run hello world executable that we just built, and there you go. Though so it doesn't look very nice. Though hello exit is simply the rest is. Let's change this string. String is not looking very good right now at this point. So we'll go to hello world DT, and though let's remove the word hello. So though x86 assembly is there, rust is easier. Okay, and we do this again, and we execute. So first we build here the object file .o. This line over here, this NASA minus f help, use the assembler to take that assembly file and generate .o, the object file, and then you call linker with telling it, hey, I want to generate it for i386 architecture, 32-bit. You give it a .o, and then you give it the run minus o. And I think minus s, you guys probably want to take a look at what is minus s corresponds for. But okay, but in any case, we got our executable, and now let's see that. Though x is there, is there. There you go. So at this point, Arjun was very happy, very, very happy. And then he said, but I want more. As you know, he was always little bit dissatisfied with the world. He thought the world was a place where there was not much meaning, because ultimately what would he do with all these pleasures that he would get by knowing high level languages? So he said, let's do a little bit of, he wanted to see the ultimate reality. So Krishna showed him CPU architecture and assembly, but still he wasn't happy. He said, respected sir, we want more. I want more. So then Krishna actually said, you know what, let's do a parity program. So what's the parity? How do you calculate parity of a 32-bit number? You start in, this is in C by the way, and then we'll go to assembly. But right now we are doing this in C. I want you guys to not immediately get confused by the assembly code. So you first start to get to live in illusions. So anyway, this is as close to the reality, I would say, as it gets. You got you start with a parity equal to 0. Now the 30, remember what is get parity? Parity is the number of 1 bits. So if you got odd number of bits in a number, then you got odd parity. If you got even number of bits, you got even parity. So we return 0 for even parity and 1 for odd parity. That's what we are doing in this program. We start with a local variable. Now we use while n. While n, what do we do? We keep flipping parity to not parity. Whenever we see there is, we get one bit at least. Because you see, the loop will, if you enter while loop, it's because at least 1 bit is set. And then we flip, and then we get rid of that 1 bit by, as you know, n equal to n and n minus 1 clears the rightmost 1 bit in n, right? We know this KNRC, and we can also actually prove that. If you just think about it, like 3 is 1 1 in binary, right? 0 0 blah 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 1 1, and 2 is 1 0. So if you do 3 and 2, what happens? You ended up with 2. Basically, it clears the rightmost 1 bit, and you can do with other numbers. So we use this algorithm, and when we run out of no bits set, all the bits are cleared. This is, then we return whatever is the parity, however many times it was flipped or not. So this is a much better algorithm to calculate parity on a 32-bit number than to, just brute force keep shifting by 1 and keep ending with 1. That way you may have to do it like 32 times. But if you have a, this kind of logic, then you will only do for as many times as there are 1 bits in the number. So that's our parity. Now let's try to do this in assembly, because remember, we are actually trying to see the ultimate reality now. So now in assembly, we have this program parity.asm. This is the same program that we had last time, but we had to add a function now, get parity. Now I will try to explain to you guys what does this function do. So this part, str and those things, they were just like in the previous program, no big deal. We can see that we have a global label here, parity. This would be in C kind of, or high level languages will be like a global variable or something like that. And this is label, we are saying, hey, we would be using this. This is where our function will store whatever the return value the function will put in this place at parity, this 4-byte value. dd means 4 byte. You can have db, you can have dw, you can have dd. See, this one is like saying, hey, the bytes, db stands for bytes are starting here. Now, so this is our function. What does this function do? If you are familiar with x86 assembly, you will realize that here we are saving the stack, we are pushing the current frame pointer, we are moving ESP into EBP, we are making space on stack for local variables. That's why we are subtracting ESP by 16. Now what did we do here? What do we see here? D word EBP minus 4H. So this is the local variable that we had over there, parity. This is that local variable parity there in that get parity function. And what we are saying here is move 0 into that. We are initializing the local variable to 0. Now we jump to label 2. And what we see at label 2, we compare D word. Now here, what is EBP plus 8H? So you got to understand what is happening. So EBP is where your previous EBP is, and then you got, when you do a call, so now you see the main program, or because we don't have a main, we have a start actually. So here you see this part is the same, that hello world is still printed. Then we have this number with 9 bits set in it. You can actually check it out. You would see that this one, I think the 7, I think the 5, the one with 5 has 9 bits set in. Yeah, so this one has 9 bits set in it. Now we are pushing the argument on the stack. This is a typical calling convention. You got to understand the calling convention on x86. So the arguments have to be pushed on the stack. The function call is made. We call the function. This is how you call the function in assembly. When you call the function, the return value is automatically pushed on the stack. So that is why EBP plus 8H is where your first argument is, not at EBP, because you got old EBP, then you got the return value, then you got the first argument that you pushed here in the caller. This guy is the caller. The start is the caller. See here, you push the only one argument, so we push it on the stack. Push call get parity. Now what did we do here? Why are we doing this? Add EAX in 30. Now this is a very crucial point, because the return value is put in. Now let's look at, did it really do? We can see that function put the return value of parity, that local variable that we were saying return parity, that's actually moved to EAX. So EAX is where the return value of the function is, but EAX is just a number, 0 or 1, right? So, and you can't, there is no system call that will print the number by itself. We got to convert the number into ASCII value. So that's why we are adding 48 or hex 30 into EAX. And then what did we do? We took that EAX and we put it at this location parity, where you see in the beginning we had a label known as parity in data section, which is basically like a variable. And we actually put that result of the calculation in that location. And then we also added a new line because we want to exit cleanly, and we also so as you know, for to store 0 and 1, or just here this 1 byte, we don't need all those 4 bytes, so we can use the other bytes. Parity plus 1, new line. Parity plus 2, we put 0 to null terminate. So now we have converted the parity label, those bytes at the address where the parity label is, into our ASCII, into a buffer where ASCII string is there instead of just a number. So that will be easy for us to print. So then what we did, then we can just repeat our previous thing that we learned how to print hello world. We just 4, we moved 4. You know why we moved 4 to EX? Because 4 is the right system call number, and 1 is the exit status. We put the address of the buffer we want to print into ECX. That's why we put that location parity. Now in this case we only want to print 4 bytes, so length of the string at parity, and then we again executed the system call. This is how in x86 they used to do syscall, because remember the syscalls were interrupt gate. The interrupt gates used to go through interrupt hex 80, and this is where we do the exit system call. So let's try to run this program and see if we get what we want. So let's do that. So parity.asm. Okay, great. Now we're gonna use the linker to build our executable. So we will say parity dot minus o parity, and then parity dot o, and it did link. Now let's see what it did, and we got 0 here. Now why did we get 0? How do we know this value is correct for the parity? So because this is assembly, we don't have the luxury of taking the input from the command line. So would it actually have even number of bits? Let's see that. So we have some programs here that can tell us in C++ and all. Okay, let's build this G++. What does it do, by the way? Before we build it, we say test1.cpp. So the test1.cpp basically for us, it will give us the binary representation of that number. So let's look at, we'll just build it. Hopefully it will build with C++ 11. We say test1.cpp minus o test1. That's the executable name. It built. So let's look at test1. We give this number. So it didn't take it. Okay, it wasn't happy with that. What we're gonna do is, let's see. It wants a decimal number. Let's give this number that I wrote here. It's a big number. And we see that this number in binary is this. So now as you see, this number is 394.27 hex. It's basically got 3 bits here, 4, 5, 6 and 3, 9. So the parity should be odd parity, right? So in that case we have to modify our parity.asm program. Instead of 7, let's do 5. We want to verify that it is giving the correct result. So 5 is not good. 7, and we know it should have the odd parity, so it should return 1. So let's do that now. We build the .o, parity.o, then we build the executable like this, and then we said execute that. And there you go, we got 1. So it is correctly calculating the um, parity in assembly. If you want to see verify this more, we can do this. So it doesn't like these, none of these programs like in C or C++ like to enter numbers in. So let's put it this only. Give the input in decimal, and there you go. It's saying the number of set bits is equal to 9. That we also verified here in binary representation. But I just wanted you to see that even the C program is giving it the parity as odd parity, because in 9 bits as said 9 is an odd number, and that's why our assembly program is also giving us the parity as 1. And with that, let's look at the assembly program again. So this is where Arjun's eyes were opened when he came to know that that assembly, you got to know each and every register, you got to know the CPU very intimately. So I explained to you guys little bit of here, like what is the meaning of this EVP minus 4H, which has a local variable parity, and EVP plus 8H is our argument, is n that we passed n. But basically the algorithm, if you think about it, what was it? It was go inside the while n and keep flipping the parity local variable. This is what you are seeing here. You see, when we used to do n and n minus 1, this is where the end is happening. See, n minus 1 is happening here. EX, you are subtracting from EX. This is n minus 1. This is n, the variable that you passed, and every time you keep you ending it, then you compare that with 0. Is it 0? Argument has after doing n and n minus 1, has it become 0? If not, you jump to label 1 again. This is our while 1 loop, that while n loop. Remember that there was a while n loop in C program, parity.c. See this loop, while n. In assembly, where is this? If you see in assembly, the loop is here. See, when it jumps back to label 1 after comparing d word, this is actually the argument that we passed. And this is where you are seeing things like what is going on here, if you think about it. Comparing d word, the local parity, this is basically reciting, flipping. The earlier part here is flipping. Whenever you see EBB minus 4H, which is the local variable, it is basically flipping that guy. This is where this flipping SAT, like if the previous thing was turned out to be 0, or comparison resulted in 0, the success, then you just set AL. So you set AL1, and then you move, then you sign extend AL into EX. Now here you say you subtract, and then what you do is you move that n variable, the argument, into EX. You subtract 1, that is n minus 1. Now n and n minus 1 is here. See, this is the assembly way of saying n and n minus 1. And that's what you assign to n, right? You basically, then you compare, this is where now the new n is, you compare that with 0. If it is not 0, you go back to your while n loop. So this is, assembly can be very, very in detail, because there are no abstractions here. You know you're working with CPU, you're working with registers. But after Arjuna saw this, when Krishna showed Arjuna this assembly, and Arjuna got to see the CPU in raw, and he saw how what is happening ultimately when these higher level languages actually execute on the CPU. His eyes were completely opened, and he was illuminated by the reality of the world. And with that, he attained self-realization. So I hope this program would help you to attain self-realization. in programming, and you would not be limited to the abstractions of the high level language, but would also be getting familiar with with the way the CPU works, and you would know what is a stack point, what is a stack, what is a stack pointer, what is a things, how do you compare, how do you loop in the assembly, how do you refer to a global variable in assembly, like in our case parity, how will you or str, how do you make system call directly in assembly, not having to do in so you would know the mystery behind what happens when you keep doing printf, and why if you don't add this 30 into eax and try to print eax as it is, suppose we didn't have this step, then would it print? Because you know what will happen, the ex will have either 0 or 1. Now 0 or 1 by itself has not much significance in terms of ASCII. So if you really want ASCII 0 and 1, meaning the character 0 and 1, not the number 0 and 1, then you got to add hex 30 in it. So this is a very important point. But with this kind of detail, when you handle, when you work at this level of detail, your eyes get open to the computer architecture, and you got to see how things work, and then you attain self-realization. And Arjun was very happy. Krishna gave him all the blessing that he needed to go and perform in this world and win the war of understanding computer programming and languages and CPU architecture. With that, adios, and I'll see you guys next time. Bye bye.